So our halogenation reaction here is basically a substitution, right? So thinking SN1, SN2, a lot of those reactions happened in one or two steps. Reactions of alcohols tend to take a few more steps, but let's go through an example here. So there's a couple ways to do a halogenation of an alcohol. One of them is with phosphorus tribromide, PBr3. That'll add a bromine on in place of the alcohol. PCl3 works as well and follows the exact same mechanism, just with chlorine instead of bromine. And so in this case, take an alcohol, react with PBr3, dichloromethane here is just the solvent, not taking part in the reaction. Right, and then we're doing a one-for-one swap here, basically. Our alcohol group is now replaced with the bromine, right, to go on and do other reactions. So the mechanism here looks a little complicated, but there's not too much to it. In organic chemistry, using a phosphorus might be a little bit rare, but essentially our alcohol, oxygen adds to the phosphorus, pushing off a bromine, right? This two-arrow bond formation, bond breaking step is basically an SN2 step, right? And now we've got a more complicated group here, but if we take a look, we've got carbon skeleton, oxygen, hydrogen, that's all still there. But now we've got this new bond between oxygen and phosphorus here. It's connected. Oxygen also has a positive charge now, and bromine a negative. So we've essentially made it a good leaving group, right? And this next step is another SN2 to get the product, right? So we're generating Br minus as our nucleophile to attack and push off this alcohol bonded to phosphorus, which is now a good leaving group here, right? And that's our mechanism, essentially an SN2 step followed by another SN2 step to activate that. So this is SN2. In this case, my example is not drawn with stereochemistry, but remember that would flip the stereochemistry if possible there.